Before Dan starts his presentation, I wanted to ask him a couple questions about himself. So first of all, what do you do? Can you explain to the audience what you do for work?
Well, I'm a geologist. I work for the U.S. Geological Survey. I'm focused on volcanoes, so you could call me a volcanologist. Specifically, I work on keeping track of what we call ground deformation at volcanoes. Volcanoes, as I'll explain today, swell up and shrink, and they react to things going on underneath them. And I use various techniques to measure those movements and try to understand what they're telling us about what's going on under the volcano.
Great. And we'll hear more about that today, I assume.
We will.
Excellent. So how did you become interested in science? You've had a good career at it, but how did this all start for you?
I grew up way back in the 1950s and the 1960s. It's a long time ago. But back then, the first satellites hadn't even been launched into Earth orbit. So I was in grade school when that happened. I found that very interesting. The first planetary probes got sent to places like the Moon and Mars and other planets, and we got pictures for the first time of other worlds. Nobody had ever seen that. I was excited about that. I decided when I was about 8 years old I wanted to be a spaceman. And so I went to school and I studied science, and I still wanted to be a spaceman. And I went to college and I got a degree in physics. And then I went to grad school, still wanting to be a spaceman, study the planets. And my advisor went to a meeting in Hawaii. I'll say a little bit about Hawaii in my talk, where there are active volcanoes. And he came back from the meeting and said, "Boy, Dan, you need to go to Hawaii. If you're going to study other planets that have volcanoes, you need to go to Hawaii because they've got active volcanoes there, and there's a volcano observatory right up on top, and you should go." So I went, and immediately I fell in love with volcanoes because I realized that the most interesting planet, and the only one I was ever really going to get to, was the Earth, and it had volcanoes on it, and I had a chance to study them, and I became a volcanologist, still am.
So it wasn't until you were in your 20s that you realized you were going to become a volcanologist?
That's right.
Okay.
When I was in grad school, I really focused on volcanoes.
What is it that you like about science?
You learn things that nobody knew before. I mean, I've been so lucky. I have a project in Yellowstone. Yellowstone is known as the supervolcano. And I go there, or I used to go there, and I would make measurements about how much the ground surface was going up or down. And in a matter of a few days, I could start a survey, and myself and 3 or 4 other crew members would be the only person on our planet that knew that over the last year the surface of the ground had gone up a half an inch or down a half an inch. And so you learn new things, and then you ask yourself, well, why did that happen? And then it really gets interesting because you say, well, I think it happened because the geysers are pressuring up. And so you make some measurements to see if that's true. It's not. So then you say, well, maybe it's because magma is accumulating. Well, if magma is accumulating, then this should happen. So you go make that measurement. And you get to a better understanding of what's going on in the world we live in. I think that's just really exciting.
Well, it's amazing the kind of things that we can learn through science. And I think your presentation today is going to talk about some pretty amazing stuff we've learned through science. So let's get you going here.
Okay.
Take it away. Let's try it again. There we go.
There we are. Okay. We've talked about me. Let's talk about something more interesting, volcanoes. Did you know that there's a volcano in Hawaii that's been erupting continuously for 30 years? It's called Kilauea. It's been in the news recently because one of the lava flows is coming into an area where there are homes. The scientists, of course, are trying to give as much information as they can to the people who might be threatened. There's another volcano in Hawaii called Mauna Loa. It's the biggest mountain on the Earth. It's even bigger than Mount Everest if you start at the base of Mauna Loa down under the Pacific Ocean up to the top, more than 30,000 feet high. And it's an active volcano. It's going to erupt again, too. In Alaska, there are at least 50 potentially active volcanoes. We don't hear a lot about them because they're kind of remote, but they can put ash in the air that can affect airliners. So we keep close track of them too. And in the Pacific Northwest, Washington and Oregon State, we've got a dozen active volcanoes. We call them the Cascade Range. Mount St. Helens, Mount Hood, Mount Rainier, you might have heard of. We as scientists think of them all as being active volcanoes. They're active because they've been erupting on and off for hundreds of thousands of years, and there's no reason to think they're going to stop anytime soon. So we say they're active. We've got plenty of volcanoes in the United States. Not everybody knows that, but it's true. But I've got a question for you. Do any of our volcanoes actually move? And I'll tell you the answer. The answer is yes, they do. They get pushed around, they swell up and they shrink, and I'll explain some of the reasons for that as we go. My next question for you, though, is a little bit harder. What do those volcano movements tell us about what's going on deep inside the Earth? If you pay attention, you'll be able to answer 3 questions that I'm going to be asking you, and you'll get a chance to answer them a little later on. So, about 50 years ago, only 50 years ago, I'm a little older than that, scientists discovered that the Earth's surface, including the part that's covered up by the oceans, is broken up into big pieces that we call tectonic plates. There are 15 big plates and a whole lot of small ones. I live, and some of you live here in the Pacific Northwest, but all of us, including those students who are with us from Alabama, live here on the North American plate. We've got a couple of nearest neighbors to the west, the tiny little Juan de Fuca plate and the much bigger Pacific plate. So here's a map that we can animate, and it'll show us how the plates move and how volcanoes fit in. Watch what happens when we cut an imaginary slice through the map and put the plates in motion. This is going to go pretty fast, but in the real world, what you're going to see takes millions of years. So here we go. At the plate boundary over on the left, new oceanic crust forms where lava erupts onto the surface of the ocean, and the plates spread apart at an average rate of a few inches every year. Where the plates collide near the middle of the slide, over here, the Juan de Fuca plate dives under the North American plate in a process called subduction. So if we zoom in on the subduction zone, we see that some of the water that got carried down in the Juan de Fuca plate is released. It causes the melting point to drop and we form magma. Where the plates get stuck to one another, the North American plate gets shoved to the east and bulges upward. Eventually magma that forms reaches the surface and feeds our Cascade volcanoes. So things are moving all the time. The most recent eruption in the Cascade volcanoes was at Mount St. Helens from 2004 to 2008. By the way, if there's time at the end, ask me about the last big earthquake in the Pacific Northwest. It's a neat story that I'd be happy to tell you. I can't tell you right now. But first, let's get to your first question. The question is, on average, how fast do the Juan de Fuca and the Pacific plates spread apart as a result of tectonics? And Ray, are you going to give me a hand here?
Yeah, let me go back here. It's a little clunky to go back and forth, but we'll bring the poll up here in 1 second. Bam, there we go.
Okay, how fast do the plates spread apart? A few inches every million years, a few inches every year, or the plates don't move. They're made out of solid rock. So now you get a chance to vote for the right answer.
We'll take about 1 minute, so as a class, decide what the correct answer is, and we'll see what people think. Well, we've got 5 votes then. Everybody listen, like they're on the same page here with this one. We'll give you another 10 seconds. All right, we got all 6 votes here. Looks like 6 out of 6, 100% of people thought a few inches per year. Let's go back to the slideshow and see what the answer is.
And the right answer is, of course, a few inches per year. So you're all right. Either you guys were paying attention or you already knew that. That might not seem like much, just a few inches a year, but that means that in a million years is like the blink of an eye to geologists like me, they spread apart by more than 60 miles, or in the metric system, that's about 100 kilometers. That's a long way in a million years. So the new space that gets created as they spread apart, it gets filled up by new oceanic crust that forms because we have those eruptions on the seafloor. And so where does the extra crust go? Well, it gets subducted at the other end of the plate. It dives underneath the North American plate in this case. So if you think about it, we're living on a giant conveyor belt. Luckily, it doesn't move very fast. If the conveyor belt moved a lot faster, we might get subducted down into the mantle or spit out of a Cascade volcano, and we wouldn't want that. So now let's move on and talk about how and why volcanoes erupt. Remember, magma forms beneath the North American plate as the Juan de Fuca plate gets subducted and starts to melt. That magma rises and it collects in something we call a magma reservoir underneath a volcano. I've shown that reservoir just as an orange ball here. It's really more complicated than that, but this will work for us. So the magma fills up that reservoir. When the reservoir can't hold anymore, it ruptures, and the magma escapes toward the surface. When it gets to the surface, it produces a lava flow or a lava dome, or in some cases, an explosive ash eruption. All 3 types of eruptions, lava flows, lava domes, and big ash eruptions, have happened at Mount St. Helens during its history. So let's trigger our own eruption here. Here we go. Volcano erupts. This looks like a lava flow eruption, and the reservoir refills. So did you notice what happened? We can do it one more time. As the volcano erupts, the reservoir shrinks, the volcano goes down, then the reservoir refills, and the volcano gets pushed up again. I've exaggerated that motion so we can see it more easily in the slide. But it happens in the real world, and we can measure it. In the real world, volcanoes might go up and down by an inch or a fraction of an inch. In the last eruption at Mount St. Helens from 2004 to 2008, the biggest movement was just about an inch. That happened at the Johnston Ridge Observatory, which is about 5 miles away from the volcano. That's about 2.5 centimeters of movement, about 8 kilometers away in the metric system. If you haven't been to the Johnston Ridge Observatory, I realize you folks in Alabama would have a long way to go, but if you get a chance, I suggest you go to Johnston Ridge Observatory or JRO. Here's the view. You're looking directly into a big crater that formed during the eruption in 1980. On a clear day like the one you see here, you can see the volcano, you can see lava domes in its crater, you can see a glacier. And even if it's a cloudy day, there's a movie and lots of exhibits that you can look at. If you pay close attention, you might even see me in one of the exhibits. But let's get back to the volcano story. We've learned that the Earth's surface is broken up into about 15 big plates. They're constantly moving, they're colliding, they're subducting. The magma that forms causes volcanoes to shrink or swell as magma moves in and out of the reservoir underneath. Here's something to remember. The movements of the ground surface that we talked about, together with earthquakes and volcanic gases that volcanoes give off, like carbon dioxide and sulfur dioxide, they allow scientists to recognize when a volcano is getting restless and when it might be getting ready to erupt. That allows them to give warnings to people like us who might be at risk from an eruption. So, are you wondering how we measure those very little movements at volcanoes? I'm going to talk about that, but first, I've got a second question for you. The question is, name 3 things that scientists measure to predict eruptions. And Ray will get your answers.
just a second here. All right, here we go. So what three things do scientists measure to predict eruptions?
Okay, plate tectonics, subduction and spreading ridges, magma, lava, and ash, ground movements, earthquakes, and volcanic gases, or none of these things. Scientists can't really predict eruptions. Okay, your turn to vote.
These are all pretty good answers, except, yeah. All right, another 15 seconds to get your vote in. Everyone's in agreement so far. 6 out of 6 votes. Going for ground movement, earthquakes, and volcanic gases. All right, back to the PowerPoint. And we will see what the correct answer is.
Well, the correct answer, of course, is ground movements, earthquakes, and volcanic gases. Either I'm a good teacher or you guys are pretty smart. I think
nice work, people. Nice work.
Probably the latter. Good job. So how do scientists measure those teeny little movements at volcanoes? Well, the answer is we use everything we can think of. I've used lasers, GPS, tilt meters. I've even used a tape measure. We use radar. I'm going to talk about radar in a minute, but first let's think about another problem. How are we going to make these measurements safely at a volcano that's dangerous? We figured that out about 10 years ago when St. Helens was getting active again. And you might be surprised by the answer. We use spiders. Yeah, we use spiders, but it's a different kind of spider than you're used to. Here's a volcano scientist version of a spider. It only has 3 legs instead of 8 like the other kind, but it has lots of other stuff on it. There's a GPS antenna that helps us to keep track of where the where the spider's going. Now you might be wondering how this kind of spider walks around on steel legs. It doesn't. But imagine that we take this spider, we put it on a volcano that's moving, the spider moves with the volcano, and so we can use the GPS on the spider to figure out how much the volcano is moving. We could also put a seismometer on the spider to measure earthquakes. We could put a gas sensor there to measure things like carbon dioxide and sulfur dioxide. We've even put cameras on spiders so we could take a look at what was going on. Of course, we're also going to need some batteries inside to run everything, some electronics to make it work, and we'll put a radio antenna out here on the spider so we can send all that data back to the Volcano Observatory where it's safe and where we can analyze those data. Okay, so now we need to take our spider to the volcano. We're going to need a helicopter. Let's see if we can make that happen. Here we go. All right, we're in the helicopter. We're all suited up. We'll take off. There's our spider. We've got it on a tether. It's got a smiley face there. I guess it's happy to be going to the volcano. We'll lift it off. Go! Okay, we got it. All right, up we go. We're going into the crater at Mount St. Helens. It's wintertime, plenty of snow up there. The crater is just ahead. We're coming around the northwest side. There's one of the older lava domes there. That's where we'll put it. Now, we don't want to put it in a steaming area where it might get too hot, and we don't want to put it on snow because that's not very stable. And we want to know how much the volcano itself is moving. So, there's a good spot. We'll set it down in the rock, and we're good. No, but we're still hooked up to the spider. Maybe the pilot can take care of that for us. Can you let go? There we are. Okay, our spider's in place. It's sending signals back to the observatory where we can analyze them. Now, let me see if I can get back to our PowerPoint. I hope you had a lot of fun with that. I did. You know, when we put that spider out, we had the doors off so we could see exactly where we were setting it. So I had to make sure that my seatbelt was fastened. So now let's talk about a new way to measure ground movements that doesn't even cause us to have to go to the volcano. We do it from satellites. They orbit the Earth. It's got a fancy name. We call it INSAR. You don't have to worry about what that means. It's not important. What's really neat is how it works. So imagine that this is a satellite with a radar that can bounce signals off the ground surface and record the signals that come back. I know it doesn't look like a satellite, but I'm a scientist, not an artist. Just imagine. Some later time, the satellite flies over the ground surface again, does the same thing. Maybe in the meantime, there's been a big volcanic eruption or an earthquake. So we get a second set of data. Scientists compare the two sets of radar data, and they make a picture of which areas moved and how much. We call that picture an interferogram, and it shows the movements of the ground surface as bands of colors. So let's launch the satellite and see how that works. Here we go. Our satellite comes in over the ocean, doesn't see very much. Get to the coast, not much going on. But here, there's been a big earthquake causing those color bands. And here, that stripe of color means we're crossing a big fault, maybe the San Andreas Fault, and that fault has moved a little bit. So this is what we're able to do from radar satellites orbiting the Earth to measure little bitty movements of the ground surface. Even a small fraction of an inch. It's not magic, it's just science. But how do we use INSAR at volcanoes? Well, here's the same volcano we saw before. Instead of the magma reservoir down below, I've shown the color bands that we would see in interferograms during, between, and after an eruption. So let's see how this works. The volcano erupts, we see a pattern of colors, it stops erupting, we don't see much, and then it fills up again, and we see a pattern of colors. Let's do that one more time. Volcano erupts, we see colors, it stops erupting, and now in the interferogram, when the reservoir fills up again, the volcano swells up, we see it as a pattern of colors in the interferogram. We also use GPS, we use tilt meters, other kinds of instruments to measure ground movements. But I can't talk about all those things. I've got to ask you a third and final question. That question is, what causes the surface of a volcano to swell up before an eruption? Is it magma filling a reservoir a few miles below the surface, volcanic gases, or radar signals from satellites in orbit? Your turn to vote.
All right, here we go. Again, what causes a volcano to swell? Magma filling a reservoir miles below the surface, volcanic gases, or radar signals from satellites in orbit telling it to swell?
All right, I see the votes coming in.
Are you guys talking to each other? The same answer? What's going on here? Everybody is on the same.
Next time I'm gonna ask harder questions.
All right, we'll give you another 10 seconds to cast your votes. Well, it looks like everybody is voting for magma filling a reservoir miles below the surface. All right, that was the last poll question here. Let's go back to the PowerPoint and see what the correct answer is. Back to you.
And of course, you guys are right. The right answer is magma filling a reservoir below the surface of the volcano causes it to swell up. I wasn't able to fool you guys with any of those questions. So now it's time for you guys to ask me questions. I hope you've enjoyed what I've told you about how volcanoes move, and now when your friends ask you, you ever heard about volcanoes moving, you can say yes, it's a result of plate tectonics and magma coming in and out of a reservoir below the surface. Thanks.
All right, thank you. All right, here. So go ahead and if you want to enter your questions down below. Let's see here. I'll get the camera back working. Doesn't seem like it is working. All right. Well, first question from Mr. Penner's class at Castle Rock High School. Do gases also make the mountains swell?
You're a very smart student. The answer is yes, because one of the debates we have about some volcanoes, and I'm thinking about Yellowstone caldera right now. Yellowstone, of course, is a super volcano, and it goes up and down a lot. And I've spent the last 30 years studying it and trying to understand why it goes up and down. And even with all those years of study by not just me, but a lot of scientists, there's still a debate as to what role gases might play in uplift at Yellowstone. There's good evidence that the hydrothermal system, the hot water system beneath Yellowstone can seal up a layer because you get minerals depositing and they fill up all the cracks. It's also, of course, very hot, just a couple miles below the surface, so hot that the rocks can kind of anneal themselves and fix any cracks. And we know we've got magma coming in from down below. As the magma gets closer to the surface, the gases come out of the magma as bubbles, and those gases collect, and they can pressurize the area below that area that's got all the fractures sealed up. And there's good evidence from geologists that those pressures can get high enough to actually lift the surface. So the answer is yes, gases might play a role in causing volcanoes to swell up. So why do volcanoes go down? Well, you can imagine that there's an earthquake that fractures through that layer that got sealed up, and the gases escape, and we see the volcano going down. So it's a very good question, and the answer is yes. Gases can play a role. Gases come out of the magma. Volcanoes are more complicated than I've described them to you. And that's one of the reasons they're so fascinating, because there's so much going on. There's magma involved, there's gases, there's the hydrothermal system, there's tectonics, lots of other things too.
I did not know that. Very cool. Well, we've got a question from Birmingham, Alabama. Do volcanic eruptions always cause an earthquake?
Almost always, because if you imagine what an eruption is, magma is coming from inside the earth and getting to the surface. How can it do that through solid rock? Well, the answer is it has to break its way through. It has to break rocks. And when it does break rocks, we see earthquakes. It makes different kinds of earthquakes. We see earthquakes caused by rocks breaking. We see earthquakes caused by magma vibrating. We see earthquakes caused by gases streaming up through magma. So almost always we see earthquakes before and during volcano eruptions. In science, you find that there's often an exception to every rule. A few eruptions seem to have happened without any earthquakes. But maybe there weren't seismometers in the right place, maybe they weren't close enough, etc. So the answer is almost always yes. Eruptions are accompanied by earthquakes.
A question from Tukes Valley Primary. How long did the Mount St. Helens eruption last? I suppose there's 2004 and also the 1980. Maybe you could talk about both of them.
Sure. Well, in 1980, of course, the volcano at Mount St. Helens became active for the first time in over 100 years. It erupted in the first big eruption on May 18th, 1980. There were some more explosive eruptions during 1980, and then we started to build a lava dome in the crater. And the lava dome grew on and off until 1986. So that part of the activity lasted about 6 years. Then the volcano went to sleep for about 18 years. We knew it was still active. It was still going to erupt again someday. And sure enough, another lava dome started to grow in 2004. And that eruption went on till early 2008. So between 3 and 4 years, the latest dome building eruption lasted. A
couple questions, or at least one question about the spiders here. How do winds affect the spider? Is it pretty resistant to winds up there? And does it have to deal with high winds? What's it like in the crater?
Well, it can be, the weather can be severe in the crater. We can get a lot of snow, we can get high winds, we can get ice. And it's a great question because the first spider that we put up at St. Helens, we didn't put legs on it. We just had a footlocker with instruments in it and some antennas and things. And guess what? It blew over. So once we saw that, we figured, well, we need to make it more stable. So we'll put 3 legs on it, kind of like a tripod. And we've had better luck with that setup.
And how long does it take to build a spider? And who built it?
Some folks where I work at the USGS Cascades Volcano Observatory came up with this idea. And the first one probably took them a week to put together, and now, of course, they've built a lot of them, and they're good at it, and they can put them together in different configurations. As I said, the gas scientist among us might want one that has a gas sensor on board, and so they'll design one for that purpose. But then maybe I'll come up with the idea, well, I want to get a time-lapse photography of the lava dome growing. So can you build one that is set up to have a camera on board and to send the pictures back once a minute or something? So they can build them up pretty quickly. They've done that, and they've actually shipped spiders around the world for volcano scientists elsewhere to use.
Wow. Another question from Alabama. Well, it's asking, do you only study volcanoes?
Volcanoes are my main interest, but when you study volcanoes, you find that you have to be interested in other things too. You have to be interested in earthquakes, of course, because as I said, volcanoes are part of the whole story of plate tectonics. Plate tectonics also causes big earthquakes. So I'm interested in earthquakes, especially how they relate to volcanoes. I'm interested in geology in general. I mean, the planet we live on is a fascinating planet. It's at least as interesting as Mars and Mercury and Venus, because a lot's gone on. And so I'm interested in geology, and the part of geology I spend most of my time studying is volcanoes and volcanic activity.
Well, another question one more from Alabama. This comes from Sam in Birmingham. He wants to know, have you ever been near a volcano while it's erupting? If so, how close? I'll add to that. Have you ever had any other hairy moments while working that are some pretty exciting stories? Maybe it's a good opportunity to tell us a story here.
Well, yes, I have been at erupting volcanoes, but I've been safe in every case, I think. And that's obviously a big concern. We don't want to take risks in order to get the answers to our questions. So we understand, we think, a lot about how volcanoes operate, how they work, what parts are dangerous, what parts aren't. So I've taken my rock hammer and taken a sample of lava as it oozed out in a lava flow at Hawaii. I was standing a couple feet away. I've even made lava spoons where you put a spoon on a stick and push it into the lava and twist it around and fill your spoon with lava. I've been at Mount St. Helens on the lava dome when it's been getting ready to erupt, but those eruptions tend not to be explosive. Magma is sticky and pasty and doesn't have a lot of gas in it, and it moves out fairly slowly. So yes, I have been fortunate to be close to volcanoes while they've been erupting. More dangerous volcanoes, of course, you get your instruments in like spiders or other instruments and you get out of the way.
Good question from Mr. Penner here. He says that he's heard that major weather systems can affect the altitude of the ground. So how do you deal with this when also looking at magma-caused movement of the surface or deformation?
Another very good question. You guys are good at this. There are other things that cause the ground surface to move, and we have to be aware of that. The earth tides cause the ground to go up and down, for example. And so we can predict how big that signal is, and we can correct for it in our measurements at volcanoes. Great big, strong weather systems what is a strong storm? A strong storm is an area of very low atmospheric pressure, so that there is less atmosphere pressing down on the surface of the Earth, and as a result, the surface can respond. Those kinds of movements, weather-caused movements, are pretty small, even smaller than the movements I've talked about. So we generally don't have to worry about them. The exception is INSAR, the radar interferometry, because in that case, the weather systems can produce color bands that look like the ground surface has moved, but they're not really. They're caused by the atmosphere. So we have ways to try to identify those signals and take them out.
Oh, wow. Well, that's pretty cool. Never thought about that. Looks like we got one last question here from Wilson's class at Tukes Valley Primary. How does the data get from the spider to the researchers? And then, yeah, we'll start with that one. There's one more question, too.
Well, good question. We wouldn't want to be up there with our spiders at some of the times they experience when there are big rock falls or eruptions or in really terrible weather. So the answer is we send all the data back by radio. And we send those data back to the Volcano Observatory. In this case, for Mount St. Helens, that is the Cascades Volcano Observatory. It's located in Vancouver, Washington. It's about 50 miles away as the crow flies. Those data all come back into the observatory. They come into our computers. They get analyzed. They get corrected. They get modeled in some cases. And the scientists there work together to interpret what they mean. And
people who are working on the spiders, where do they actually work? When they're getting the data, where are they physically?
They're at our Volcano Observatory. We have a group who specializes in instrumentation, coming up with new ways to make important measurements at volcanoes. And so the nice thing is I can walk down the hall and I can talk to Rick, who is the guy who came up with the spider idea. And I can say, hey, Rick, can you make a spider that will do this thing for me? And he'll say, well, yeah, let me think about it. I'll see what I can come up with. It's nice to have a group of scientists together, all interested in one problem, because some of them are better at some things than others. If they want to know something about ground information, they might come to me, but if I want to know something about radio telemetry, I go to Rick.
Cool. One big team.
Yes, that's right.
Well, I just want to say thank you very much for being here today. Thanks to all of you out there for taking part in this Volcano Explorers. Before you go, I want to make sure that you fill out the survey. We really need your feedback on this. But again, thank you. Thanks to all of our other partners, ESD 112, U.S. Geological Survey, U.S. Forest Service, and Chevron. And keep your ears out. We're going to be doing more of these next year. We haven't set dates for them yet, but we've had a great time and look forward to doing more of these. So hopefully we'll see you back here at Volcano Explorers. Have a great weekend and great holidays, and we'll talk to you soon. Take care.